We will talk today about the AI thirst and how data centers are draining our grid and water. We live in the age of artificial intelligence, from the large language models that write our emails and code, to the generative AI that creates art and videos, to the complex algorithms that drive scientific discovery. This technology is reshaping our world. But this incredible power does not come from thin air. It comes from massive, city block-sized buildings called data centers. And while we interact with AI in the digital cloud, its physical footprint is very, very real. So today, we are pulling back the curtain on the immense environmental cost of the AI revolution. We mean the voracious appetite for two fundamental resources, electricity and water. This is not just a tech story, but it is a story about our energy grid, our water supply, and the future of our infrastructure. Let us first talk about the AI power hunger. You might have heard the statistics. A single AI-powered search query can use almost 10 times the electricity of a traditional web search. But to understand why, we need to talk about the two phases of an AI's life: training and inference. Training is an incredibly intensive process of creating the AI model. It is like teaching a single, massive brain by feeding it virtually the entire internet. This requires thousands of specialized, high-powered computer chips, GPUs, running flat out for weeks or even months. The numbers are staggering. Training a single large language model, like GPT-5, is estimated to consume more than 1,000 megawatt-hours of electricity. That is enough to power over 1,000 average European households for an entire month. And that is just for one model. But training is just the beginning. Inference is where you and I use the AI, asking ChatGPT a question or generating an image with Midjourney. While a single inference uses far less power than the training process, the scale is mind-boggling. With hundreds of millions of users making billions of requests, the inference phase now accounts for the vast majority of an AI model's lifetime energy consumption. This has led to a parabolic rise in demand. Data center hubs in places like Virginia's Data Center Alley are seeing their power demands double in just a few years. Utility companies are scrambling, and in some cases, delaying the retirement of fossil fuel plants to keep up. The AI revolution is, in real time, stress testing our power grids. So what is the AI hidden thirst? If the AI power hunger was the obvious part, the thirst is the hidden crisis. All that electricity running through servers generates immense heat. If that heat is not removed, the hardware melts. So, how do you cool a digital furnace? You use water, a lot of it. Most large data centers use evaporative cooling systems, and this process is incredibly water-intensive. A large data center campus can easily use millions of gallons of water per day, the same amount as a city of 30,000 to 50,000 people. Let us put a face on that. A recent study revealed that Microsoft's global water use spiked by over 35% in a year, largely driven by its AI investments. In Council Bluffs, the Google data center campuses requested over 1.5 billion gallons of water in a single year for their cooling needs. That accounted for over 50% of the entire city's water usage. This creates direct competition for resources, especially in drought-prone regions. This means when an AI data center draws water from the same aquifer that farmers use for crops or that communities use for drinking, it forces a difficult conversation about priorities. So, let us explore the perfect storm and the domino effect. We have an explosion in AI demand, but it is hitting a system that is already under strain. We are facing the perfect storm for our infrastructure. Alongside the AI boom, we have a resurgence in U.S. manufacturing, from semiconductor plants to battery factories, which are also massive energy and water consumers. At the same time, we are in the early stages of the electrification of everything, such as electric vehicles and heat pumps, which further increases grid load. The domino effect is real. In places like Northern Virginia, the world's largest data center hub, the local utility, Dominion Energy, has had to revise its forecast dramatically upward. It now predicts that data centers will make up over 40% of their total electricity demand by 2030, up from just 10 to 15% a few years ago. This forces utilities to find power, and fast. The cheapest and fastest solution is not always solar or wind, but it is often natural gas, or even coal. This creates a cruel irony. The technology of the future could be locking us into the dirty energy of the past. So what are the solutions and the path forward? This all sounds pretty dire, right? But it is not a hopeless situation. The tech industry, engineers, and policymakers are aware of the problem and are racing for solutions. The path forward lies in three key areas: efficiency, location, and innovation. Efficiency is about smarter chips and better code. Location is about knowing that geography is destiny. Innovation is about a radical new cooling system. First, efficiency. Chip designers like NVIDIA are relentlessly focused on creating more powerful, but also more energy-efficient GPUs. Just as important is software efficiency, writing better, leaner AI algorithms that can do the same work with far less computational power. Second, location. This is critical. We will see a push to build new data centers in places with abundant, carbon-free energy, like geothermal-rich Iceland or hydro-rich Quebec. More controversially, companies are looking at water-scarce but cooler climates, like Scandinavia, where they can use outside air for cooling most of the year. And third, radical innovation. This is where it gets exciting. Technologies like direct-to-chip liquid cooling and liquid immersion cooling are game changers. Instead of using air conditioners, these systems submerge servers in a non-conductive fluid that absorbs heat 1,000 times more efficiently than air. This can reduce cooling energy use by 90% and eliminate water consumption almost entirely. Beyond that, we have the ultimate goal: using the waste heat itself. In a few forward-thinking communities in Europe, data center waste heat is being piped into district heating systems to warm homes and businesses. It is a move from being a drain on resources to becoming a part of the community's utility infrastructure. The AI genie is out of the bottle. It promises to be one of the most transformative technologies in human history. Yet, we cannot ignore its physical cost. The question is not whether we should stop AI, but how we can build a sustainable AI ecosystem. The choices we make now in how we power and cool these digital engines will have profound consequences for our climate, our water security, and our energy independence. It requires smart regulation, corporate responsibility, and continued public pressure. The future of AI does not have to be a story of blackouts and drained reservoirs. It can be a story of innovation that pushes us toward a more efficient and sustainable world. But that future is not guaranteed. We have to build it. What do you think? Should there be stricter regulations on where data centers are built? Are you willing to wait an extra second for an AI response if it uses 50% less energy? Let us know your thoughts in the comments below. If you found this analysis valuable, please hit that like button and subscribe for more content that explores the impact of technology on our world. Thanks for watching.